We're looking at the last page of the 9196 worksheet 2, number 30 here. Uh, so we see that this is an alternating series. So as long as we can show that this rule of sequence will go to 0, then that's enough to show that series will converge by the alternating series test. So here we see the denominator will grow at a faster rate than the numerator. So by compared with growth rate, we know that limit of the rule of sequence will go to 0, and then each subsequent term will also decrease for all j values. So series converges by alternating series test. 31, 5 to the k over 3 to the k plus 4 to the k. Here, I think it's probably best to go through direct comparison test. The goal is to try and represent this as something that is simpler and recognizable in terms of something that we can easily determine as a converging or diverging series. So if we try and simplify this a little bit, or try to round this to something that is easier to handle, what if we convert this 3 to the k to 4 to the k? So if we compare these two rule of sequence, we see that the denominator here is less than this denominator. So there's inverse relationship. The denominator is less than another denominator given everything else is equal. Then we know the fractional value will be greater than the term that has the larger denominator. So we know that this is the relationship here. And the nice thing about this expression is that we can simplify this to be 2 times 4 to the k. And if we write this 2 times 4 to the k, then we can think of this as 5/4 to the k value, or 1/2 times 5/4 to the k. Now all of a sudden this becomes something that we can recognize as a geometric series, and we see that the ratio is 5/4, which is greater than 1. And if the ratio is greater than 1, then we know that the series will diverge. And because we have a series, we know the series will then diverge, and anything that is greater than a series that diverges must also diverge. So therefore we can say by geometric series test, by direct comparison test, the series will diverge. 32, we see that we can represent this as a rule of sequence that's raised to the nth power, and any expression that where the entire rule of sequence can be raised to the nth power, then we can root test is probably the best fit. So we can write this as evaluate the limit as n approaches infinity for the nth root of this expression. The nth root and this exponent n will cancel out, leaving us with just 2n over n squared. As n approaches infinity, this expression will go to 0 by comparative growth rate. N squared grows at a faster rate than 2n. So if it's equal to 0, that's less than 1, so therefore series converges by root test. Okay, 33, sine of 1 over n. Property of sine of 1 over n is that this is roughly equivalent to 1 over n. Okay, so if we know this property here, it makes it a little bit easier to simplify and to make some generalizations. So if we replace sine of 1 over n as 1 over n, then we can write this as 1 over n times square root of n, and 1 over n times square root of n is 1 over n to 3/2. So if we think of this as a comparative comparison test, since we have something similar, then we can take this expression divided by something that we know, whether it is a series that is by p series, which is converging, since p is 3/2 is greater than 1. So if we can show that this gives us a real number, then we know that this series must also converge. So if we take this original series divided by something that we know is also converging, simplify this a little bit, we get limit as n approaches infinity of n times sine of 1 over n. N times sine of 1 over n, we can rewrite it as 1 over n in the denominator. And in this expression, we can just, as n approaches infinity, we can simplify this to be n approaching 0 of t over t, since essentially n approaching infinity is going to cause this to go to 0. So what if we just represent this as a different variable as t approaches 0? We know that these are the same, it's just that a little bit easier to determine what's happening here. So limit as t approaches 0 for sine of t over t, using one of the trig properties that we know for limit, we know this will go to 1. And if it goes to 1, that's a real number, and so therefore we know that since the series that we're trying to compare with converges by limit comparison test, we know this original series must also converge. Okay, 34. 1 over n plus n cosine squared n. So if we try and compare this with cosine squared of n, we know that cosine squared of n is less than 1. And also we know that n plus n cosine squared n is less than n plus n. N plus n, we know diverges by, this is a harmonic series, and so if this diverges, and we know that this value must be greater than, okay, since this is less than n plus n, so we know that this denominator is less than this denominator, so we know that this full expression must be greater than this expression. We know that this diverges, and so this must also diverge, and this is greater, and so anything greater than 1 over 2n must also diverge. So by direct comparison test, our series must diverge. Here we have an entire expression raised to the n squared, so we can think of this as a candidate for root test. So limit as n approaches infinity, nth root of this expression, the n and n will cancel out, leaving us with limit as n approaches infinity for n to the n, m over n plus 1 to the nth. Okay. And this expression, we should be able to recognize this as essentially the same thing as e. Okay. Well, if we write this as 1 over n plus 1 over nth power, okay, if we flip the denominator, flip the fraction and the denominator, we can rewrite it as something that we can recognize. 1 plus 1 over n to the n as n approaches infinity is essentially e. So this is the same thing as saying 1 over e, and 1 over e converges, is less than 1. So by root test, since our resulting expression is less than 1, our series will converge. Okay, we'll skip 36 and 38, and we'll finish with 37. So the nth root of 2 minus 1 to the nth, we see that this entire expression is raised to the nth power. So let's use the root test. Limit as n approaches infinity of nth root of this expression raised to the n. The nth root and n will cancel out, leaving us with just 2 to the 1 over n minus 1. Limit as n approaches infinity of this expression will eventually this 1 over n will go to 0. 2 to the 0 is 1, so 1 minus 1 is 0. 0 is less than 1, so the series will converge by root test.